So, in the previous class, we introduced basically Coulomb's law and nothing else, right? And then we started using it in problems. And we didn't finish this problem. Let me quickly remind you what we have in this situation. We have two identical masses, basically point masses, charged. And the goal is to find the value of the charge, of course, of one ball, and of course charges is the same, so you'll have charge of both balls. Then what is given? Mass of the balls is given. Length of the cords, you see both masses are connected with strings or cords and attached to the same point in the ceiling. Then they are released or were released, and of course they repel each other, and of course after short period of time they reach this static equilibrium, right? So that's the situation we discussed, and also we started discussing. And also we could easily measure the angle between the vertical line and the direction of the cord. Okay, so that's what the situation. And then we started discussing the strategy of this problem, right? Where should we start, right? And I told you that any motion can be described by Newton's second law. That's pretty much the role of Newton's second law in physics, right? And in our situation, since we don't have motion, but no motion, or since a no motion is a special case of a motion, we can use Newton's second law. But of course, we need to make a decision which mass we're going to use, right? Because here, what does it say? If you apply net force on mass m, you need to take a particular mass, particular object. And of course, that object is going to accelerate with acceleration a, right? So I decided to use this mass, right? This mass will just exert an additional force on the chosen mass. So we're basically discussing no motion of that mass. Okay, so no motion, it means acceleration equals 0. So a is equal 0, and as a result, we ended up with the equation where these problems, where we should start in order to solve problems like this. And again, I told you at the end of the class, this problem is effectively physics 1 problem. Problem about static equilibrium. And the only difference that here in physics 2, we have one of the forces is an electric force. Right, so one of the forces is an electric force. Okay, so now we ended up with this equation, and now we see what needs to be done. We need to identify all forces acting on our mass. Okay, so, and that was the last piece that we did in the previous class. So we identified that there is a gravity acting on that force, tension from the cord, and the electric force which comes from this mass. There's nothing else acting on that mass m. So as a result, I wrote down in a vector form this equation. So electric force plus gravity plus tension must be equal 0. So all these forces must balance each other out. Okay, so now naturally we need to keep diving deeper and deeper into this equation until we will reveal the whole truth, and only then we will be able to see how we can extract information about the charge. But for now, we just started from something fundamental and keep diving deeper and deeper and deeper until we will see everything about this situation, about this problem. So now what's next? How many equations do we have inside of this equation? Since we have two-dimensional situation, right, so we have an x and y direction, right, everything happens in a plane. So, of course, we need to write this equation. It's a vector equation. We need to extract two equations. We need to balance all the forces in the x direction and the y direction. So all the natural steps, okay, where are my markers here? So let me start with balancing y components. I can write something like sum of all y components must be equal to 0. Right. And then I will write similar for the to balance all x components. Okay, now let me write down explicitly this equation. So we need to get all y components of all these forces. Okay, so let me start probably with tension. Since this angle theta as well, right? Because we have two parallel lines and one line intersects them. So this angle and that angles are the same. So now we can find the y component of this force. Of course, it will be, we need to find side, okay, adjacent to the angle. Adjacent, in order to find adjacent side in the right triangle, we need to use cosine function, right? You remember we were refreshing it yesterday. So it will be tension times cosine of angle theta. So, and that component, you remember, is positive because that component will be pointing in the positive y direction. Right? So this force goes into the equation with plus, so it will be Ft times cosine theta. So that's the first. Then there's no contribution from electric force because that force is in the x direction. There is no y component. It's just zero. And mg is purely in the negative y direction. So that force goes into the equation with minus mg. So minus mg equals to 0. So that's our first equation. Now let's do the same for the x components. So we need to balance all x components. I'm getting closer to the bottom of the board and it's more and more difficult. I have here a flat surface, more and more difficult to write. All right, so let's do the same for the x components. Let's start with the electric force. It's purely in the x direction, positive x direction, so it goes into the equation with plus. It will be plus Fe, so it will be electric force. Then force of gravity doesn't contribute anything. Okay, zero contribution, right? Because it's purely in the y direction. Tension, in order to find x component, the x component will be in the negative x direction, right? So it will be Ft times sine of angle. So and minus Ft times sine of angle theta. Okay, that's it. So it must be equal to 0. So we have two equations, equation number 1, equation number 2. Okay, have we revealed everything in these two equations? Not completely. Look, we still have some hidden information inside of electric force. Inside of the electric force, still there are plenty of information which needs to be open or revealed, right? And of course, what can be used in order to write electric force? Coulomb's law, right? Because we have 2-point masses. So we can apply Coulomb's law immediately, directly, right? So let me write Coulomb's law. All right, underneath, so it will be F electric equals K. Charges are the same, Q and Q, so it will be just Q squared. Okay, somebody posted something in the chat. Let me quickly check. Although again, guys, yeah, I record the classes. Again, guys, I don't check chat often, right? So just easy, it would be easy if you just say something. So Q squared divided by, okay, the distance between point masses, R squared, right? R squared. Okay, now let me open my explanation box and write down the distance between these two masses. We need to write it down in terms of what is given, or maybe some unknown. So R, this R, it's the distance between this and that. Okay, let me use some different color. Okay, yeah. So this is R, right? So now we need to write this R in terms of what is given in the problem. And it shouldn't be difficult because we have a symmetry relative to this vertical line, and this distance and this distance are the same. Okay, in my picture they're slightly different, but of course in nature they are the same. So and so how can we find this and that? This part can be easily found if you look at this triangle, this point, that point, right? It's a right triangle, and we just need to find a side which is opposite to a measured angle. what can be than that, plus hypotenuse is given L. So this distance, this side will be L times sine of angle. You remember, in order to find the opposite side to a given angle, you need to use sine function. So this will be L sine theta, and exactly the same story in this with this side and with this triangle. So it will be L sine theta. So the whole R is 2L sine theta, because we have two parts. Okay, so now I can write here in my explanation box this information. So R equals to 2L sine theta. And I will close my explanation. Okay, I don't like this overlapping. Okay, so now electric force have this expression. So K Q squared divided by 2L sine of theta n to the power of 2. Okay, we almost revealed all the information, the whole truth. So now let me just rewrite this equation with this expression for the electric force over here. Right, yeah, probably I will write there. And see what can be done with that, with this equation. So the first equation I will just rewrite without any changes. So it will be Ft cosine theta minus mg equals 0. And the second equation, of course, I will use what we just got, right? So k q squared over...
You're writing a bit off screen.
No, it's not off screen. You need to make a right click and first choose the fit the screen.
I fixed it.
Yes, because I checked the camera before the class. Everything is in the field of view, right? Okay, great. 2L sine theta. And there's another trick, annoying trick, which Microsoft Teams uses. Sometimes the picture sort of follows the speaker. If you see something like this, I move to one side of the screen, and sort of like it feels like camera follows me. It can be annoying, right? So again, right click and choose the option, I think, fit the frame, and it will stop doing that annoying feature. Okay, squared. All these sort of like short tricks of Microsoft Teams I described and posted in Blackboard. Right? You can see that. This electric force minus Ft sine. Minus F T sine theta equals to 0. Okay, so now we have equation number 1 and equation number 2. System of two equations. Now, is this enough in order to solve the problem? Let's start counting. Basically, let's start counting unknowns. How many unknowns do we have in these equations? Tension, unknown. We need to. It's not given, and in our set of equations, it's unknown. Angle is given, mass given, g is given. So 1. Then k is given, q. Q, second unknown. It looks like we have tension and Q. Given, again, this is the same unknown, and this is given. So we have two equations and two unknowns, Ft and Q. From the mathematical point of view, it's awesome. So it means that you can solve this system of two equations for tension and the charge. So at this point, I can say that physics is over. We applied all physical ideas, all physical concepts. Now the rest is just algebra. You have a system of two equations, and we revealed the whole truth about the system. And now it's just mathematics, simple algebra. Okay, so now let's see what can be done. Okay, let me write that down. So we have two equations plus two unknowns, and that is great. basically after this is just algebra. So let's see what can be done. Let me get first tension from the first equation, plug it in the second, and as a result, we will end up with one unknown Q. Okay, let me write that down. So first, from the first equation, I will get that Ft equals to mg divided by cosine theta, and then put it in the second equation. So as a result, I will put it in the second equation, and this term with minus, I will move to this side with plus, right? To the right-hand side. So as a result, I will have from the second equation, it will be kq squared, I'm just rewriting this, 2l sine theta squared. And this term, as I said, I will move to this side with plus, and I will use ft. So it will be equal to mg divided by cosine theta. I will just use this. And now times sine theta, it's at this sign. Right? Sine versus cosine, it's a tangent, right? Okay, let me show it. So this will be a tangent function, right? And so our unknown is here, right? So we need to express that. So we'll just move everything, this to that side, this in the denominator, and we will get q. Okay, and then you need to take a square root. Okay, I will take square root immediately. Okay, let me do it step by step, right? Without skipping steps. 2l sine theta squared divided by k. It's this factor on that side when I move. Of course, this downstairs will go upstairs, and this numerator will go into the denominator on the right-hand side. And then this, it will be mg and tangent theta. Okay, so now simple simplification. Let's extract the square in order to get sort of the final, the simplest form of the answer. So it will be 2l sine theta and then square root of this mg tangent theta divided by k. So that's the algebraic expression of the answer. Let me check if I got what I was planning to get. Yeah. Okay, so now you just need to plug numbers. L is given, angle is given. Don't forget to convert grams into kilograms. Right? I think it's obvious. And K, yeah, we introduced it yesterday. Right. So again, if you plug numbers, you will end up with Q equals 0.75 microcoulombs. That's the answer. In your homework, there is a very similar problem. I would say almost identical problem, right? But what is given is different, and what needs to be found is different. So basically, physical situation exactly the same. But in your homework problem, charge will be given. And what you will have to find, you will have to find angle. Otherwise, problem is the same. So it means what? It means that you need to start from the same idea, write almost the same equations, right? Almost everything will be quite similar up to this point. And in your problem, Q, of course, given, angle is unknown. So you'll have two unknowns, tension and the angle. And then problem gives you a hint. It says that assume that this angle is a small angle. Whenever you see a phrase like this, it means that they suggest you to use a well-known expansion. Maybe some of you haven't used it. Some of you probably familiar, Taylor expansion. If an angle is small, okay, that's I'm talking about problem 2262. Okay, let me for homework problem 2262, because if I don't give these explanations, students struggle a lot. I will get usually tons of emails, right, asking for what needs to be done. So let me write this. If theta is small, then you can use what is called Taylor expansion. It means that if you have sine of angle, and if angle is small, then according to Taylor expansion, it will be very, very close to the angle itself. Sine of theta equals approximately to theta, but, very important but, this angle must be in radians, not degrees. So it means when you use this Taylor expansion in your equations, replacing, for example, this sine of theta will be replaced with theta, your theta will be in radians. It means when you solve your equation for theta, your answer will be in radians. Don't forget that. And look also in mastering physics in which units mastering physics wants to see an answer. If it wants to see in degrees, convert from radians to degrees. It's not that difficult. So, but this in Taylor expansions, theta is in radians. Don't forget that. Because again, in the past, plenty of emails from students when they solved the equations and they thought that answer was in degrees. As a result, they were confused. Why mastering physics didn't accept their answer. Then, if you have cosine of angle, then it's approximately equal to just 1. And if you have tangent of a small angle, it's approximately equal to the angle itself. Again, theta must be in radians. So that's what you need to use in your problem, homework problem 62. Otherwise, it's a very, very similar problem, and the strategy is almost the same. Okay, enough of this problem. It's a nice problem, sort of like a small bridge between physics 1 and physics 2. Okay, so now after this, let's move back to new material. Okay, not back, let's move and start discussing new material. So now the goal is we need to introduce the idea of the electric field. Okay, now let me switch to the presentation. Okay, so next logical step after we introduce Coulomb's law, now we need to introduce the idea of the electric field. Very, very important. One of the fundamental ideas in physics. Okay, the idea of the field. And of course, in this case, it's an electric field. It's the end of chapter 22, beginning of chapter 23. I need to bring slides forward. Second. Okay, so these are the sections, and let's move. So what's the idea? How can we get to the idea of the electric field naturally? You remember in physics 1, we introduced, okay, you introduced in your classes tons of different forces in physics 1, right? And we divided them in 2 categories. First category we called contact forces. Sort of like tension, friction, normal force, what else? Okay, I cannot recall. But anyway, so everything is reasonably simple in terms of kind of understanding them, right? Understanding how they work, because there is a direct physical contact, right? And it's easier to comprehend, to get the feeling of these forces, right? So in order to exert tension, of course, the cord must be connected to an object, right? And then you can exert that force. Friction, again, two objects must be connected, right? And then there is a direct physical contact. And of course, two objects exert forces on each other, friction force. Normal force, the same, right? So no troubles with this. But what about forces like that? Force of gravity. So we have the Earth and the Moon, and of course the Earth exerts the force of gravity on the Moon. And in this case, there is no direct contact. It looks so mysterious. It looks so strange, right? Or a situation like this, when you have two point charges, right, repelling, no touching, again, no direct contact, but nevertheless, electric force is somehow still being exerted. Of course, very mysterious. And of course, these mysterious forces triggered in the past and still triggers lots of completely logical, deep questions. For example, like in this case, right? So, what's the mechanism? How it all works? Right? Are they exchanging some particles, or maybe some waves, or maybe they distort space, or how fast it happens? Right? Is it instantaneous, or it takes some time? Tons of interesting, fundamental questions, and almost none of those questions can be answered, right? And still, right, the same situation. So what do we usually do in the cases like this when you cannot answer a question? Politicians, they're very skillful. They usually start answering a different question, for example, right? Or they will walk around the answer in circles, right, without actually answering the question, right? Physicists, they do sometimes something similar, very tricky idea stuff. They just sweep all these questions under a rug. But that rug must be very fancy, very nice Persian, right? So no one would even dare to lift it and get those questions one more time, right? So what do I mean by sweeping under the rug in this case? So physicists, in order to avoid answering all these questions, they introduced a sort of direct contact by introducing the third party. What do I mean by the third party? So we have the Earth. It's the first party which basically exerts force on the Moon. I discussed this situation. Of course, the Moon also exerts force, but that's a different problem. Let's take this problem. The Earth exerts force on the Moon. So the Earth is the first party. The second party is the Moon, which experiences the force. And the third party, it's a sort of like a gravitational aura, or we can give it a fancy name, gravitational field, which is created by the Earth. And this whole space is filled with that gravitational field. So now, once you introduce this idea of the field, in this case, gravitational field, so now the Moon has a sort of direct contact with the field where the Moon is, and the field is created by the Earth. So now we have a direct contact, and we can sweep all these questions. We can avoid answering all those questions. Of course, you can still be sort of persistent and keep asking those questions, right? But anyway, so now by introducing the idea of the field, now you have a direct contact between the object which experiences the force and that field. So now, sort of, we move to the case of contact forces, right? Sort of artificially, right? So that's the idea of introducing fields. Of course, you can introduce a gravitational field. You can introduce in this way electric field, or maybe temperature field. You can introduce lots of different fields, right? So that's the idea. That's how we can introduce idea of the field on the level of blah 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 blah. But again, for us, for science majors, engineers, right, it's not enough. We need to be, and we want to be quantitative. We want to introduce some expressions, formulas, so we can get some numbers, so we can compare different fields. We can say, okay, this field is stronger, this field is weaker, this point this way, this point that way. So we want to be quantitative, and we need to introduce some kind of formula to be happy, right? So how can we introduce an expression and how can we to define electric field, to measure electric field, right? Okay, so how to define an electric field properly now. So let's try to come up with the definition of the electric field, and of course we need to introduce some arbitrary system, and then using that system we will try to actually define the electric field, right? Okay, so let's assume that we have this simplest situation, a point charge, Q capital, which creates this electrical aura, electrical field. Okay, I couldn't come up. Okay, this is the source of the field, and then aura or the field, this cloud. Okay, so then what does it mean define electric field or measure? Basically, it means that you need to measure field or probe electric field, right? So what does it mean probing electric field? It means that you need to have some device, probe device, which you can insert and in order to detect that field, right? Like a thermometer. If I want to measure the temperature in this room, I need to grab a thermometer, position it at a certain point, and that will be my probe system, right? So now I have to introduce a probe system in order to define field at a certain point. And of course, usually the probe system must be as simple as possible. And of course, that probe system must be sensitive to the present, in this case, of the electric field. So what can be used as the probe system? Probe charge, simple point charge. And of course, since we use it as a probe system, we are going to call it probe charge. Nothing can be simpler than that, right? Okay, so let's use this point charge as a probe charge. So that's the situation. And now, back to which expression can be used to define the electric field. How many expressions do we have so far in physics 2, in electricity and magnetism? Not much, right? Except for Coulomb's law. Okay, let's try to test it. Let's see, can we use Coulomb's law? Right there, Coulomb's law. Since we have 2-point charges, we can use it. And let's try to use it in order to understand what is not good about Coulomb's law in this case, and how can we, or how should we adjust it in order to introduce the electric field. Right? Okay, so now let's imagine this situation. For example, me and one of you work for the same boss, and he or she, boss, right, gave us an assignment, right? The work, go and measure the electric field at this point, right? Okay, so I go first. Let's say I check my pockets, right? And let's say I have a point charge. Again, it's a green. I need to find some different balls, right? 1 Coulomb probe charge. Let's say I have in my pockets a 1 Coulomb probe charge. Okay, okay, different gender, but okay. All right. Let's say I use one. Yeah.
You keep saying probe charge. What do you mean by probe again? I think I missed that.
Again, every time, whenever you want to measure, for example, temperature in this room, right? You need to use a probe system. Some object which will be sensitive to what you want to measure and which will give you some number, right? So it allows you to probe something at that particular point. So in this case, we want to measure the electric field. We want to probe electric field, for example, at this particular point. Of course, you can use some complicated device to measure the electric field. But why should you use complicated device if you can use as simple device as possible? In this case, point charge can be that device to detect the presence of the electric field or to measure the electric field. Right? Measuring probe, it's basically a device which allows you to measure something. In this case, at this particular point. Probing, measuring, detecting.
Yep, that makes sense. Thank you.
Okay, great. All right, so I've pricked, let's say I happen to have 1 Coulomb charge. That's my probe system, my probe object, right? Probe charge. I position it at this point. Okay, miss it. This point, right? And let's say I measured, since we decided to use Coulomb's law, right? So I use that expression and I can calculate or measure. Let's say I measured 1 Newton in this case. Okay, so I will write my report. So at that point, the field is 1 Newton, right? Okay, so then one of you, goes and you check your pockets, right? And let's say you have 5 Coulomb charge. 5 Coulomb charge, that's your probe charge. You go to the same point, position your charge, and let's say in this case, of course, naturally, the force will be 5 times stronger. You will get 5 newtons. Okay, so let's say you decided to use that as your number to define the field. Okay, so you will write your own report. We give our reports to the boss. Boss will look at these 2 reports, and first reaction will be what? Are you guys crazy? How come that the value of the electric field at the same point has 2 different values? It's impossible. It doesn't make any sense, right? Because a field must be uniquely defined. It means that if you take a single point, there must be a single number connected to that point. Not 2 numbers, not 3, not 100 numbers. It must be uniquely defined. In our case, if we use Coulomb's law, we can get as many numbers as we want, because we can use different probe charges. So it doesn't make sense to use Coulomb's law directly. So it means that Coulomb's law must be adjusted somehow in order to define electric field properly. How can that be adjusted? Look, what if I take a ratio, for example, of force versus the probe charge that we use? In my case, I will get 1 newtons per coulomb. In your case, again, you will get 5 versus 5. You will get 1 newtons per coulomb. So you see, in this case, it doesn't matter which probe charge you use. Every time we will end up with the same number, unique number. That's why electric field is introduced using this formula. It's the force acting on the probe charge which you use divided by the value of the probe charge. Basically, your measurements of the electric field must be probe charge insensitive. So probe charge must be removed from the game every time. In this case, your electric field will be uniquely defined. And it doesn't matter how big or how small your probe charge is, right? Which you have in your pockets, right? Okay, so that's how electric field is introduced, but it's not the whole story. We need to impose some additional restrictions. Which are those? Well, look, electric field, it's a vector. It has a strength and direction. Let's look at the direction. You remember, charges can be positive and negative, right? So if I position here, if I use here, for example, positive probe charge, of course it will be repelled from the source of the field, and of course, as a result, electric field will be pointing that way. Okay, away, right? Electric field will be pointing away. But if I use negative charge, of course, that charge will be attracted, of course, force that way, and of course, electric field will be that way. So you see, we will have ambiguity. Electric field might point in different directions, which is not good either. So we need to remove this ambiguity from the very beginning. And how? We can impose a convention. Again, bunch of old guys get together somewhere in a nice hotel in Florida and say, let's use only positive probe charge, and we will force the rest of the world to follow the same convention. So from now on, so if you see somebody reports the electric field, it means that that person used a positive probe charge to measure, to probe, to define the electric field. So probe charge must be positive by convention. So it's a first restriction. A probe charge must be positive. But it's not, again, the end of the story. What else must be imposed? Imagine this situation. These barely visible tennis balls, right? Let's say this charge creates an electric field. Let me move it here. Yeah. Then this is my probe charge. Let's say this is 1 coulomb and this is 1 coulomb. If I position my 1 coulomb probe charge over here, what will happen to the charge which creates this electric field? Of course, they interact, right? And of course, this charge which creates the electric field, because of the force exerted from the probe charge, this charge which creates the field will just fly away, right? Fly away, it means what? You basically destroyed the system, electric field of which you wanted to measure. Okay, not destroyed, significantly changed, significantly altered. And of course, this shouldn't happen. Because, yeah, of course, any measurements in physics, right, in science, right, of course, whenever you measure something, you slightly change your system, value of something of your system, right? But of course, every time when you do that, those changes must be as small as possible. Right. For example, let's say I have a bucket of water and let's say we want to measure the temperature of that water. We're not going to use a gigantic thermometer. When you stick it in, the temperature of water will be significantly changed by the temperature of your thermometer, right? Of course, every time you will take a small thermometer, put it in. Of course, that small thermometer will change the temperature of water, but slightly. It will be within experimental error, right? And those slight changes, yeah, it can be accepted. Okay, it's good for our life, right? But of course, every time, whenever you measure something, you change that something slightly by your probe system. The same it happens over here. So in order to sort of preserve our system, which creates the electric field, your probe charge must be small relative to the charge which creates the electric field, so that you would not change your system significantly. So it means that your probe charge must be small. Very important restriction, right? Okay, so now the second restriction, a probe must be small, right? So that the system would be disturbed significantly. Okay, so now after imposing these two restrictions, yeah, we can frame it and we can call it. Okay, so now it's a full definition of the electric field. This formula with these two restrictions, now it's a whole picture. Right. So now we introduce the electric field. Then next, what about units? And of course, you remember we use SI units. Okay, electric field. It's one of the most important quantities in physics, right? And nevertheless, there is no special unit for the electric field. So electric field units, whatever you see in this formula. Sorry. Upstairs we have force, newtons. Downstairs we have charge, coulombs. So newtons divided by coulombs, these are the units of the electric field. And now, interesting thing. In a few weeks, we will introduce the idea of the magnetic field. Very similar, right? And when we will introduce magnetic field, we will also introduce a special unit for the electric field, or for the magnetic field, sorry, for the magnetic field. It will be Tesla. So how come that we have two equally important quantities, electric field, magnetic field? From the point of view of physics, they both are great, fundamental, right, and so on. I cannot say that electric field is more important or magnetic field. No, they're equally strong, they're equally important, right? And nevertheless, magnetic field has a special unit, Tesla, in the future. Electric field does not. Pure discrimination in the world of physics. Really strong discrimination of two equally important quantities. One has special unit, the other one doesn't. How come? What's wrong with this world of physics, right? Discriminating quantities. And if you look not just from the point of view of physics, but from the practical point of view, we will be able to justify this discrimination, right? Look, Electric field, yeah, it's important quantity, but it is used mainly by hardcore physicists. The theoreticians, right? Yeah, they don't use something else. They use the electric field usually most of the time, right? But if we look at the magnetic field, and in a few weeks we will see that magnetic field is responsible for production of electricity. We will see Faraday's law and so on, and you will see that magnetic field is right there, right? If you want to describe electric current production, magnetic field must be used all the time. And since electric current production is everywhere, as a result, magnetic field must be used a lot. And of course, electric current production, everyone uses that, right? Technicians, engineers, right? Experimentalist physicists, they all use, as a result, magnetic field a lot. And in order to make their life a little bit easier, when you use magnetic field. So instead of using some complicated constructions of quantities, it's better to introduce a single unit, Tesla. Just in order, since you use it every day at this magnetic field, instead of using some complicated construction of units, it's better to give them a single unit, so that if you use something, it will be every day, lots of time, so that it will be easier for you to live, right? To live in the world of research. But electric field is used, engineers or technicians, they don't use electric field that often, maybe occasionally. If something is not used a lot, then it doesn't make sense to introduce a special unit so that people would have to remember that. So pretty much from the practical point of view, we can justify that why electric field doesn't have a special unit, magnetic field does. Because electric field is used less often than magnetic field in the practical life, in our everyday life. So that's why I created this cartoon, right? So you see magnetic field is sitting confidently and happily, right? Because it has a special unit. And the electric field is protesting, give me the special unit, right? So because of this pure discrimination, right? Right. Okay, guys, so at this point, let's have a break. It's 8:50, and from here we will basically now start using this definition of the electric field. And of course, we will use the electric field pretty much till the end of this semester, right? Almost every day. Okay, so let's have a 10-minute break. So next, okay, so now we have a definition of the electric field, right? I think it's well defined. And so now next step, what? Let's apply this definition for a particular system, and which particular electrical system. And let's start with the simplest possible electrical system, point charge. Basically, electric field created by a point charge. Let's write down an expression or formula which can be used to find the electric field. Now, of course, it's a banal, right? It's very straightforward, right? But anyway, let's say it. So let's assume that you have point charge, which creates this electrical aura, electrical field, right? So, and now we know how we can define electric field. You grab a probe charge, right? You grab the probe charge, again, small positive probe charge, position it at a point where you want to measure the electric field. Position there, measure the electric force acting, then take that force and divide it by the value of the probe charge, so that your measurements will be probe charge insensitive, right? Okay, so now, and so since we have an expression now, so we will have to take F divided by the value of the probe charge. F, it's a Coulomb's law just, right? So it will be our expression for the Coulomb's law divided by the value of the probe charge. Of course, the value of the probe charge will be cancelled. Basically, that was our idea, right? And as a result, you have an expression which we are going to use a lot in this course from time to time, right? So this electric field, okay, it's a magnitude of the electric field. It's a magnitude of the electric field, or electric field strength at the distance r from the point charge q. So again, this is only electric field expression for the electric field created by the point charge. Don't use it anywhere else. In a few classes we will introduce capacitor and something else. No, this is only for the electric field created by a point charge, because I've seen in the past on the exams when students try to use this formula for systems, which doesn't make sense. Okay, which is wrong. Right. Okay, so yeah, so this will be used a lot. Now, next logical step. Electric field is invisible to our eyes, right? And so it will be a great idea, useful idea, to come up with some lines or something, right? Which can be drawn on a paper or on a whiteboard, so we can, by just looking at that, those lines, you can tell immediately, okay, their field is stronger, their field is weaker, direction this way, direction that way. It's very, very useful. Let's come up with the idea of some lines to visualize the electric field again, because electric field and then in the future magnetic field, they are invisible. Trust me, it's very complicated. Like in my research, when I use low frequency lasers, terahertz lasers, low frequency, for our eyes, it's invisible. It's very not convenient to work on the optical table, to work with that type of radiation. Right? Okay, so first, of course, idea how we can visualize this electric field is what is called mapping electric field. Usually the first experiment, lab experiment, which students do during the normal semesters when students are at school, they map electric field. So what does it mean? For example, simplest situation, right? Point charge, which creates the field. So what you do? So this is the charge which creates this electric field. What you do? You grab your probe charge, positive small probe charge, position it at the point where you want to measure the electric field. Again, like in the previous slide, measure the force, divide by the value of the probe charge, and you can draw a vector, electric field vector. Then grab the same probe charge, move to the next point, for example, this point, do the same. Electric force, divide by the value of the probe charge, get the electric field, draw it. Then move to this point, again the same, this point the same, and you keep moving your probe charge from point to point, drawing these electric field vectors. And maybe after an hour or two, or I don't know, you can map the field and you can draw something like this. So now, it's one way of visualizing electric field. And now let's look from the point of view how many pieces of information you can extract from this picture. 2. Because electric field is a vector, of course, you need to know, okay, in two-dimensional space, you need to know 2 parameters in order to describe it properly, right? So in this case, you can, for example, see the strength of the electric field. Strength of the electric field is in the length of these vectors. The longer the vector, the stronger the electric field, right? So here electric field is weaker, there electric field is stronger. Yeah, you can see that. Then direction, again, you also see because you use the vector. So direction of the vector gives you direction of the electric field. So you can get 2 pieces of information, strength and direction. Great, it's one way. Now, of course, if you have a negative charge which creates electric field, of course, the situation will be like this. All those vectors will be, directions will be inverted, will be in the opposite. So now all these vectors are towards the negative charge, right? So it's one way. But you know what? Now let's look at this picture from the practical point of view. Let's say your work is consists of that you have to do something like this every day, several times a day. What will be your first reaction? Okay, not first, but soon you will come up with, you know what, even whenever in the class I try to draw something like this on the whiteboard, you know what, in a 5-10 seconds what I start feeling kind of annoyed, right? Damn it, it's so tedious, so boring, right? You stand and keep drawing this vector, that vector, this vector, that vector, this. It's so annoying, right? So immediately your first desire is you want to change it somehow because it's too tedious. And again, if you have to do it every day for your work, you will get angry very quickly. So I guess that was the driving force for Faraday. I guess here, a few hundred years ago, he had to do this quite often. So at some point he got annoyed, and what he did in order to simplify his life, he just, for example, grabbed this, for example, all these vectors, right? You see this vector, the next vector, and he connect them with the straight line. Straight line. Then this way also straight line and straight line and straight line. And he ended up with something like this. It's so much easier to draw these lines, and he called them electric field lines. Again, nothing wrong from the physical point of view with this, with visualizing the electric field using these vectors, but it's so tedious. It's so, yeah, you got the point, right? But when you have to just draw a bunch of lines with the direction, it's so much easier. It's so much more convenient, right? And of course, in case of the negative charge, of course, all these lines, directions of these lines will be towards the negative charge, right? So he called these lines electric field lines. That's what is used to visualize electric field. But now let's look from the point of view of getting information. So you remember from this picture, we could extract two pieces of information: the strength of the electric field and direction. Now let's look at this picture, at this way of visualizing the electric field. I can see directions, easy, right? So you can grab any point, and direction of the electric field lines gives you a direction of the electric field. But where is the strength of the electric field? There we could see, because we had vectors. The longer the vector, the stronger the field. Now we ditched those vectors, right? So now we have just straight lines. So where is the information about the electric field strength? Have we lost it? First the impression light, yeah, it looks like we lost that important piece of information, but no, not completely. We just transferred that information from one point to another point, okay, from the length of the vectors, like in this case, to the density of electric field lines. What do I mean by this? Look, over here, closer to this charge, right? So over here, density of these electric field lines is larger, right? As a result, over here, electric field is stronger. If you move away over here, for example, right? So density of electric field lines is smaller, electric field is weaker. So we haven't lost information about the electric field strength. We just moved it from, okay, we deciphered it. Oh no, we hide it in a different way. So there it was in a length of the vectors. Now it's just in the density of this electric field line. So you see, if you have a complicated picture of the electric field lines, you see, okay, there density of the electric field lines is large. Okay, it means that field is stronger over there. There, it's not very dense, so it means that the electric field is weak over there, right? Okay, so we haven't lost anything, but this way of visualizing electric field is way better, is way easier, much more convenient, right? Yeah, sometimes people lazy to do some complicated work, and as a result, they come up with better ideas, right? So that's what I guess Faraday did, right, when he introduced electric field lines. So that's why this picture, put this picture, that's better. Okay, so now we introduced idea of the electric field lines. In a few weeks, we will introduce in a similar way ideas behind magnetic field lines. Lots of similarities. Okay, so now this is an example of the simplest possible electric field lines. Now let's look at more complicated picture with electric field lines. Let's look at let's look at what is called a dipole. We're not going to use dipoles a lot, but in this case, yeah, it makes sense. What is dipole? Basically, dipole, it's a system of 2-point charges. One is positive, the other one is negative. And absolute value of their charge is exactly the same. Let's say 5 coulombs minus 5 coulombs. It's a dipole. And you see how complicated electric field lines are. So now they are not straight lines. They have this curved shape, right? And So now, of course, the question again, how can we get information about the electric field strength and direction? So now, direction. Because in the previous example, we have straight electric field lines, now they curved. So how can we get a direction of the electric field? So let's take this point. Let's say you want to know the direction of the electric field vector direction at this point, because you can see only electric field lines. So you take the point in which you're interested and draw a tangent line. So your electric field points along a tangential direction. And of course, direction of the electric field here is given by the direction of the electric field. So you see curve goes that way, so it means that electric field will be pointing along tangential direction in that direction. Right. So along a tangent line. Or here, if you take this point again, you see electric field is tangent to the electric field lines. You see, I use two terms, electric field line and electric field. Electric field, it's a vector, right? Okay, so electric field is tangent to the electric field line, right? Or this point, again, you see, it's tangent. Then, in the previous slide, I forgot to mention, you noticed that electric field lines all the time start on positive charges. And you can see it here. You see? All these electric field lines, they start on positive charge and end either at infinity or, in this case, they end at the negative charge. It's a consequence. Is it a consequence of what? It is a consequence of that you remember convention that we decided to use only positive probe charges. If we decided to use a negative probe charge, the whole picture will be sort of inverted. So electric field lines would start on the negative charge and end on the positive. But since we decided to use a positive probe charge, we have all the time this picture. So all the time electric field lines must start on the positive charge and end on the negative charge. And that's what we have over here. So you see all these electric field lines terminate at the stop at the negative charge. Then electric field strength, as I told you in the previous slide, if we take, for example, this region, you see electric field lines are not that dense, so electric field is reasonably weak. But if I move over here, density of lines is larger, so that's a region with a stronger electric field. So these pictures of electric field lines, of course, are very useful, and of course you've seen them in the past, and you will see them in the future if you're going to do any work in this field. Okay, so what's next? Let's move. Just basically sort of conclusions, which I just told you, right? And pretty much I collected all the conclusions what we just discussed, right? So you can read it by yourself, right? It's when I don't like reading from slides. Right? So now the question for you. Again, the poll is in the chat. Just scroll it up slightly. Today you were not very active, just a little bit up, and you will see that chat. And you will see the poll in the chat. So what do we have here? You see, we have sort of imaginary square. It's a square, so the sides are the same. And in two corners of this square, we have two charges, -2 coulombs and -2 coulombs. Then we are interested in the net electric field at the center of the square. This is the center of the square. And so we need to pick what is correct about the electric field at the center. Direction of the electric field at this point. A, straight up. Is it true or not? B, it points this way. C, points that way. D, direction of the electric field at that point that way. And the last option, E, electric field at the center is 0. So what is correct at the center of this square? Basically now you see we have, of course, two charges, and of course electric field, of course, is a superposition of two fields, right? So again, you remember that in the previous class, powerful principle of superposition, of course, must be used now. Okay, so give it a try. Quite often on exams, among multiple choice questions, I give a questions like this, wherein you have to find direction of the net electric field at a certain point if you have some point charges somehow distributed, right? Okay, give it a try, and then I will discuss that. And let me scroll also to the poll. Okay, I see you started discussing. We have an interesting leader. It's first time I see that leader. Okay, that option is leading in the poll. The poll is in the chat, so where you just posted, you just need to scroll it up slightly. Yeah, so it's 1, 2, 3, 4 messages. Just scroll up 4 messages and you will see the poll. That's where Microsoft Teams allows me to post the poll. A poll, any poll. So have you found? Okay, good. Awesome. Okay. I'm somewhat surprised. Okay, good. I'm just looking at your answers. Okay, let me discuss the situation. How I would do it. Actually, there are two approaches I would use. Let me bring the slides forward. Right. Okay, so let me use this picture. Right. So it's exactly the same square. So we see -2 coulombs, and that is the center. Okay, so first approach, I would use a probe charge. You remember, small positive probe charge, small so that we wouldn't disturb our system. So I have to position it, at the point where we want to find information about the electric field. So where is it? Here, positive probe charge. Right. And now, again, we have what? We have basically two fields. One electric field created by this negative charge, and the second electric field created by this negative charge. So we have, at any point, we have superposition of two electric fields. So at any point, we need to apply principle of superposition to find information about the net electric field. So let's first discuss the first field created by this negative charge, -2q, right? So again, so this probe charge, positive, of course, will be attracted towards this negative charge, and then that force we divide by the value of the probe charge, and of course it gives us direction of the electric field pointing towards negative charge. So that will be first electric field, right? Now we can do exactly the same with the second field. Again, this probe charge, of course, will be attracted to this negative charge. You remember, opposite charges attract. So you take that force of attraction divided by the value of the probe charge, how we introduce electric field, right? And of course, it will give you the electric field, second electric field. And of course, electric field strength of this one And strength of this one, they must be the same because this is the center of the square. Distances are the same. So this point is equidistant from these charges, and the values of charges are also the same. So strength of this field and strength of this field, they are the same. So now the last step, principle of superposition. We just need this. We just need to add these vectors as vectors, right? So you just complete a parallelogram, and of course you will end up with a net electric field, pure horizontal, pointing, okay, that way, pointing that way. So which is option C? Which is the option C, right? So it's a one approach. The second approach, I think, which is maybe slightly easier, right? I would imagine electric field lines, which we just discussed, right? You remember electric field lines over created by a negative charge. They are towards the negative charge, right? All the time they towards. So let's take the first, okay, first negative charge, this one, right? So of course electric field lines all the time towards it. Okay, let me use the ruler. So it will be all the time towards that negative charge. Right, so towards, okay, damn it. Right, something like this, right? So it gives us information about these electric field lines, give us direction of the electric field at the point in question. Then this charge also all the time electric field lines are towards. Maybe I can draw it, you know what, let me pull this curtain out and draw it. No, this side. Let me do it on this side. I drew everywhere. Let me erase it quickly. So we have one negative charge, right? Oh, it's overexposed. Let me move it over here. So one negative charge, and electric field lines, you remember, all the time they're towards that. Right. So our point in question is over here. So one of these electric field lines basically give us direct information about the electric field. Then we have a negative charge, second negative charge over here. And again, okay, let me use different color. So again, all the electric field lines are towards the charge. So our point in question is over here, and these electric field lines is going to give us information about the electric field direction at that point. So now you just need to add them up, this and that, and as a result, you will get the direction of the net electric field. And of course, it's not zero. It points that way. I think this is the easiest approach. Usually just recall electric field lines, and it will give us information about the electric field at the point where you want to get information about the electric field. Okay, so that's what I mean by the second approach. So as a result, the answer is C. I was surprised when I saw that it's the first time I see the second place was taken by option E, electric field equals 0. No. Electric field would be 0 if, for example, at this corner of the square you had a positive charge. Exactly the same positive charge, but positive charge, plus 2 coulombs, right? At that point, at that case, at that point, the electric field will be 0. Okay, so now let's play. What if we, okay, that is the answer. Here, follow up. What if the lower charge is plus 2 coulombs? 2 coulombs. What if this charge is replaced with plus 2 coulombs? Think for a second. We're not polling. And now let me explain. Of course, this bluish electric field will be still the same because this bluish electric field is created by this negative charge, which is still the same. But if you replace this charge with plus 2 coulombs, of course, this green electric field will be flipped with the opposite one, because you remember again, electric field lines of the positive charge, they start on the positive charge and then they go away. So it means that this greenish electric field will be flipped and it will point this way in the opposite direction. And of course, exactly the same in strength. So now if you add this blue field with this green field, of course, the net field in this case will be straight up. So answer A will be the correct answer if you change that -2 coulomb at the bottom with positive charge. Right? You see that? Now, if you change both of these charges with +2 coulombs, then of course even, green one will be flipped, and also blue field will be also flipped, and now it would point that way. So now green field will be somewhat that way, blue that way. So if you add them up, of course, the net electric field will be in direction D. Right. So that's how I would analyze these situations. And as I said, on the exam, among multiple choice questions, I like giving questions like this. Sometimes you can have 2 charges, 3 charges, 4, slightly different configuration, but that's how you should analyze problems like that. Yeah. Okay, so now probably the last slide of today's class, and then we'll move to problems. Okay, so now we can say we know how to analyze electric field, how to play with that, right? So now we can say, okay, we are experts of the electric fields. And so now, next step. What if you have this situation? Let's say you have this, I don't know, volume, this field is filled with the okay, too many fields, right? Let's say this room is filled with the electric field, right? Electric field, and you know information about the electric field at this point, at any point you want. And let's say from space, I don't know, some particle flies, I don't know, from the sun, the solar wind, I don't know, so electron flies through your room, or maybe proton flies through your room, right? So of course these charged particles are going to interact with your electric field. And of course the question is now, let's say you know information about the electric field, you know information about your charged particle which flies, right? And you want to know what will be the value of the force exerted on the charge from the field, because again, they're going to interact. How can we find electric force, which comes from the electric field and which is exerted on the charge? Very, very simple. How can we get the expression for the electric force? Basically, recall the definition of the electric field, right? You remember E = F divided by the Q. In order to get the expression for the force, just solve it for F. F will be equal Q times E. So easy. So that's how, if you have information about the electric field, and you have information about the charge which flies or which is exposed to that electric field, just multiply charge times the value of the electric field at the point where the charge is at this particular moment. Right. So this is one of the fundamental equations. Closer to the end of the class, when we will write the whole set of Maxwell's equations, right? This equation will be added to the bottom in order to have a complete picture of electricity and magnetism. So it's one of the fundamental equations. In a few weeks, we will introduce something similar for the magnetic force. This is the equation for the electric force. So there will be only 2 forces in this semester, right? New forces which we will introduce. This is the first one, electric force, and then there will be magnetic force. That's it. Right. Okay, so now let's look at a couple of easy examples, simple examples. What if we have this electric field? Now, as experts, what can you say about this electric field? And then we will introduce the special name, and we will use this type of electric fields a lot in this semester. First of all, what can you say about the strength of the electric field, this electric field? You see, direction is the same. You can take any point and direction of the electric field will be the same. It's given by these electric field lines. These are basically electric field lines which we just introduced a few slides ago. But what can you say about the electric field strength? It's the same. Because you see, okay, at least I tried to draw, to create sort of equal density of these electric field lines, right? Yeah, it looks like decent, right? So if density, since density of electric field lines are the same at every point, at every point, right? It means that electric field strength is the same. So it means that electric field in this case is exactly the same at any point, at every point. So this field is called uniform field. In this case, it's a uniform electric field. So in this course, we're going to use uniform fields a lot. Uniform electric field, then there will be uniform magnetic field. So this is the first example of a uniform electric field. Directions are the same, strengths are the same at every point. Right. Okay, and now let's just dump a couple of charges and see directions of the electric field, or electric force, direction of the electric force, sorry. Right. So let's assume first we have a positive charge. Let's say I position here a proton. What will be a direction of the electric force? You see, we have information about the electric field, we have a charge, and it's a positive charge. What's the direction of the electric force? Since, again, we just need to use this formula, right? Since this charge is positive, it means that direction of the electric field and direction of the electric force are the same if the charge is positive. So it means that the direction of the electric force will be that way if the charge is positive. But what if the charge is negative? If a charge is negative? So now, again, we will have to look at this equation. Now our charge is negative. So I can write, for example, like minus an absolute value of charge Q. So over here in front, basically, we have a negative sign. It means what? What happens with the direction? It means the direction of the electric field and direction of the electric force are opposite. So it means that in this case, although electric field points that way, electric force will be in the opposite direction. So this negative charge will experience force that way, and of course it will start accelerating that way. But positive charge experience force that way, and it will be accelerating that way. All right. So from now on, all these forces, now it's electric force, and then in the future we will introduce magnetic force. All these forces are sensitive to the sign of the charge. If this charge positive or negative, it's sensitive to that. So I will keep reminding you about that. I will keep bugging you because lots of mistakes on the exams when students are not very attentive to the sign of to signs of charges, right? So be careful now. Direction of the forces, in this case electric force, in the future there will be magnetic force. They're all sensitive to the signs of charges. Pay attention. Are you dealing with positive charge or are you dealing with negative charge? Very silly, place for silly mistakes. And quite often students sort of, they know, but sort of in the rush in the moment, they forget about that on the exam. And then when they see their mistakes, they can, damn it, how come that I forgot that this charge was negative? And they choose the different direction for the force. Okay, but I will keep bugging you about this from time to time whenever I had a chance, whenever I will have a chance. So this question I'm not going to poll. I will just maybe say a few words, and then we will start solving problems, right? What if you, for example, have these two charges, and you don't have information about what is, you don't have information about those charges. You don't know the signs, you don't know the values, right? So basically, this charge is in the black box and that charge is in the black box. So how can you get information about those charges? you can, for example, map the field. You can get the probe charge, probe it everywhere, right? And draw electric field lines. Let's say you drew these electric field lines and they look like this. So you see these electric field lines. And now, can you tell if this charge positive or negative, and if this charge positive or negative, right? So basically, which configuration of charges is correct? This is a simple question. Usually, if I had time, I ask students, but now this time I don't feel like asking you. All right, I think I'm sure that all of you already know the answer. It's just basically a question to test if you remember that electric field lines, they all the time start on positive charges and end on negative charges. Since you see on this picture direction of the electric field lines, they start on this red circle, right, and end on the green circle. It means that this charge is positive and this charge is and this charge is negative. So the correct configuration, of course, configuration B, right, plus and minus, right? And just to remind you about the fact that all the time electric field lines, they start on positive charges and end on negative charges. Okay, so I will stop my lecture at this point, and now we still have what? Oh, only 12 minutes. Let me start discussing problems. At least we will start, and then we will continue that tomorrow. Okay, let me switch to the whiteboard quickly. So this is problem 23-4. And we have 2-point charges. Physics very simple, yeah. 2-point charges. Of course, each of those charges creates its own electric field, which fills up the whole space. And of course, at any point, if you want to find information about the net field, you have a superposition of 2 electric fields, right? So that's the situation. We have 2-point charges, and we will have to find the electric field at one particular point. Okay, let me do it this way. Just trying to estimate the amount of space, right, I need. Okay, I will position here a positive charge, right, and then negative charge will be right underneath over here, negative charge. Right. Okay, and distance between them is given. I will show it in a second. We need to find electric field at this point. Right, so let me draw this dash line over here. So this is point where we need to find electric field. Let's call it point P. This distance is given. It's a B. Okay, let me use blue. B 5 centimeters, and this distance is also given. A 10 centimeters. And we need to find the electric field at point P. Okay, that's what needs to be found. Let me write it. So find E vector, basically at point P. This physical situation and geometry, yeah, we're dealing with vectors. What should I draw on the picture at some point, sooner or later? I cannot avoid drawing that important piece of solution, I can say. Whenever you deal with vectors, you have to introduce coordinate system at some point, sooner or later. Otherwise, it's bizarre. Actually, it would be, yeah, just doesn't look cool, doesn't look correct. All right, so let me introduce coordinate system. And of course, you can position the origin anywhere you want, but of course, the most convenient point is point P, where you want to find the electric field, right? I doubt that you would argue with me about that. So, and axis, you have your constitutional freedom to choose any coordinate system, right, with any directions of axis, right? But I think I will position, of course, at point P, and this will be my x-axis, and this will be, oh my god, what an ugly line. So this is y, and that is x. So that is my coordinate system. So after introducing coordinate system, I feel much, much better, right? I hope you share my feelings, right? Okay, so now yeah, I think I gave you everything. Yeah. And now let's start discussing. Yeah, basically physics, I told you right a few minutes ago. Each charge creates its own field. So we just need to draw first. I would probably draw electric field, not electric field lines, electric field vectors, right, at that point, and then I would try to add them. So let's complete the picture. Let's draw vectors, and then I will discuss sort of strategy of the solution, sort of from the mathematical point of view, or physico-mathematical point of view. So first vector, yeah, I didn't label charges. That's what now I realize. So let me call it Q1. And the value of Q1 is, now I realize what I didn't give you. Q1 is minus 6 nanocoulombs. And Q2, this is the charge Q2, is 3 nanocoulombs. Again, you remember, nano is 10 to the power of negative 9 nano. Right. So now, okay, everything is here. So electric field vector created by this charge at that point. A direction, recall electric field lines. Electric field lines all the time point away from the charge, right? So away, 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 away. Since we're interested in this point, away, it means that way. So this will be my first, how long? Okay, I will draw it like this. So this will be E sub 2, because it's a field created by the second charge. First, Q1, negative charge, again, you remember, negative charge electric field lines are towards, right? All the time towards. So since we're interested at this point, towards, it means that electric field vector, okay, you know what, let me draw first the dash line. And now I can draw electric field. So this will be E2. Oh no, it's E1, sorry. It's E sub 1. Right. Okay, and now principle of superposition. We just need to add these two vectors as vectors. And this will be our net electric field, which needs to be found. Okay, so now, yeah, everything is, the picture is complete. Pretty much everything that we need to know from the picture is there. And now, general strategy. Like first, before we start fighting the battle, we need to make a decision as generals, what will be the strategy. Okay, effectively, this, from the mathematical point of view, this problem is identical, from the mathematical point of view, identical to the problem which we solved yesterday, the first one. Right, you remember we had a few charges and we needed to find the net electric force on one of these charges. So here, from the mathematical point of view, the situation is the same. So basically we have this vector, that vector, we just need to add them. Of course, nature of these vectors are different. There we had force, and we wanted to find the net force. Now we have electric field, and we need to find electric field. From the mathematical point of view, problems identical. Mathematics doesn't care about physics, about nature of this vector or that vector. It sees the vector, it treats it as a vector. So as a result, it means that we just need to apply exactly the same strategy like yesterday. So first, can you find the magnitude of this electric field vector? Easily. We just derived, we see the direction, and of course we need to use the expression for the electric field created by the point charge. You remember, kq over r squared. So let me frame it because it's a fundamental equation over here, right? So that's what we need to use, right? So we can find a magnitude of this electric field using this formula. We see the distance, we know the value of the charge which creates this field, piece of cake. Then, once you know magnitude, can you find components of that vector? Easily, because it's all, the whole vector is in the x direction. We can find x component and y component. You see, the steps are similar like yesterday. Now, about this vector. Again, can we find magnitude? Piece of cake. Then components, if we find one of these angles, this angle or that angle, we should be able to find components of this vector. Once you found components, you have two vectors represented in the component form or written in the component form. And then you just need to, if you want to add them up, add corresponding components and you will find vector E. Right, components of vector E. And then you can find magnitude, you can find direction whenever you feel like finding. Okay, somebody post something, post it on the chat. In the chat, let me check. Oh, okay, it's from the past. Okay, so you see the same strategy. So now I will move a little bit faster than yesterday, but again, the idea is to practice electric field and again review vector algebra. Right? It's already 9:50. Right. Okay, guys, so I will finish this problem tomorrow, first thing in the morning, all right? Then a couple of additional, most likely conceptual questions, and then we will move to a little bit more complicated. We will still stay on the electric field, but mathematical complexity of problems will be increased a little bit. We will have to do some integration.